The night sky holds a secret far stranger than any science fiction. What if every star and galaxy is not a physical object, but an intricate digital projection? This is the simulation hypothesis, a serious idea suggesting our universe is an advanced construct. We are about to explore 21 cosmic anomalies, glitches in reality that challenge everything we assume about existence. You will see how the bizarre rules of quantum physics and the unsettling fine-tuning of the cosmos point toward a simulated reality. By the end of this journey, you will possess a new framework for understanding the deepest mysteries of the universe. We will investigate why particles change behavior when observed, and why the universe seems perfectly designed for life. What single observation would make you question the nature of your own reality? The idea that our reality might be an elaborate simulation is not a new fantasy but a serious philosophical argument with profound implications. Thinkers like Nick Bostrom have framed it as a logical trilemma, a puzzle with only 3 possible solutions. The first possibility is that every advanced civilization inevitably destroys itself before it can create such technology. The second is that any civilization capable of building ancestor simulations simply chooses not to, perhaps for ethical reasons. The final and most startling possibility is that we are, in fact, living inside one of those simulations right now. If even a single advanced civilization ever decided to run such simulations, the number of simulated minds would vastly outnumber the one original reality. Statistically, the odds would then be overwhelmingly stacked against us being the original biological beings. This is not about malevolent machines, but about a potential scientific discovery, a fundamental truth about the nature of existence. The search for evidence then becomes a cosmic detective story. If our universe is a simulation, it must run on some kind of substrate with finite processing power. Just as a video game has a maximum resolution to save computing resources, our own reality might have a fundamental pixel size, a smallest possible unit of space and time. This leads us directly to the first and most compelling anomaly, the finite resolution of the cosmos. The smooth fabric of reality might be an illusion. Physics points toward a fundamental graininess, a point beyond which the concepts of space and distance simply cease to have meaning. This ultimate limit is known as the Planck length. It is an almost unimaginably small scale, about 1/trillionth of a trillionth of the size of a single atom. At this level, the smooth geometry described by Einstein's theory of gravity shatters into a seething quantum foam. This is not just a small distance, it is the universe's absolute minimum resolution. You could not measure anything smaller even with infinite precision, because the very notion of smaller breaks down. This is precisely what you would expect if the cosmos were running on a finite computational engine. In any simulation, to prevent calculations from spiraling into an infinite and impossible loop, there must be a smallest unit, a pixel. The Planck length acts exactly like that cosmic pixel, suggesting that spacetime itself is not a continuous canvas but a discrete digital grid. And if there is a limit to how small things can get, it stands to reason there would also be a limit to how fast anything can move across that grid. This digital speed limit is our next anomaly, the absolute maximum processing speed of the universe. This universal speed limit is the speed of light, a constant we call c. Nothing with mass can ever reach this velocity, let alone exceed it. It is the ultimate cosmic traffic law, and from our perspective, it seems arbitrary. Why should light travel at exactly 299,792,458 meters per second, and not a single meter more or less? In a purely physical universe, this fixed number is a profound mystery. But if we are inside a simulation, the speed of light is not a mystery at all. It is a necessity. Think of it as the processor speed of the cosmos. For a simulation to run smoothly, there must be a maximum rate at which information can be updated and communicated from one point in the grid to another. If information could travel infinitely fast, the computational load would be infinite and instantaneous, a demand that would crash any system, no matter how advanced. The speed of light is the clock rate of reality, the maximum frame rate that prevents the universe from freezing up. This is why all observers, no matter how fast they are moving, measure the exact same speed for light. It is not a property of light itself, but a fundamental rule written into the operating system. This invariant constant ensures that cause and effect remain orderly, that events unfold in a logical sequence. Without this built-in constraint, the simulation would descend into chaos. This elegant piece of cosmic code leads us directly to the next set of rules, the fundamental forces that govern every interaction in our universe. The fundamental forces themselves seem to operate with a mathematical elegance that borders on the suspicious. Why should the universe follow rules that we can write down on a piece of paper? This is the third profound anomaly, what the Nobel laureate Eugene Wigner famously called the unreasonable effectiveness of mathematics. It is a strange loop of logic. Mathematics is a creation of the human mind, a system of abstract symbols and rules. Yet, it possesses an almost magical power to not just describe but to predict the behavior of the physical world with uncanny accuracy. Think of a physicist scribbling equations on a blackboard. Those symbols, derived from pure logic, can predict the exact path of a distant planet or the existence of a fundamental particle like the Higgs boson decades before a machine large enough to detect it is ever built. It is as if the universe is reading from the same script we are writing. In a purely physical, accidental cosmos, this deep harmony between mind and universe is a staggering coincidence. Why should the human brain, evolved for survival on the African savanna, be capable of grasping the profound mathematical truths that govern black holes and quarks? The simulation hypothesis offers a compelling answer. If our universe is a constructed reality, then it must run on a set of consistent, logical rules, a source code. The laws of physics are that source code, and mathematics is the programming language in which it is written. The fact that we are slowly, painstakingly learning to read this code is not a miracle. It is simply us, as entities within the simulation, beginning to perceive the underlying architecture of the program. The universe is not just described by math, it is math because it is running on a mathematical substrate. This elegant, logical backbone is one of the strongest indicators that we are interacting with a designed system. And like any well-written program, this system appears to have built-in optimizations to conserve processing power, leading us to a feature that looks remarkably like a clever bit of coding. This same mathematical elegance extends to the quantum realm, where we find a phenomenon so bizarre that even Albert Einstein was deeply troubled by its implications. He called it spooky action at a distance, a label that has stuck for a century because it perfectly captures our unease. Quantum entanglement links two particles in such an intimate way that measuring one instantly determines the state of the other, even if they are on opposite sides of the galaxy. This connection appears to happen faster than light, seemingly tearing a hole in Einstein's own theory of relativity. For a century, physicists have struggled to explain how information can travel instantaneously, violating the cosmic speed limit we just discussed. But if our universe is a simulation, this spooky action is not a violation of physics at all. It is a simple, elegant programming shortcut. Imagine a video game developer creating two objects like a pair of magic gloves. Instead of writing complex code to make the gloves communicate their status to each other across the game world every single second, a much more efficient method would be to simply link their properties from the moment they are created. The program defines them as a single entity. When you look at the left glove and see it is glowing red, the code does not need to send a message to the right glove. It already knows the right glove must also be glowing red because that property was set at the beginning. This is non-locality, a hallmark of a system that does not render every distant object in real time. The entangled particles are not communicating. They are simply two expressions of a single line of code, a predetermined variable that saves an immense amount of processing power. What we perceive as a mysterious, instantaneous connection across space is actually just the system reading from its own internal data. This quantum weirdness is more than a curiosity. It is a potential glimpse into the optimization techniques of the universe's source code. And if the program uses shortcuts for tiny particles, it stands to reason it might use similar optimizations on a much larger cosmic scale. This strange optimization for unobserved particles finds its most famous and unsettling expression in a classic experiment. A beam of electrons is fired at a barrier with two narrow slits. When no one is watching, each electron seems to pass through both slits simultaneously like a wave, creating an interference pattern of ripples on the detector screen behind. Yet the moment a measuring device is placed to determine which slit any single electron goes through, this ghostly wave behavior vanishes. The electrons abruptly begin acting like tiny bullets, passing through one slit or the other and leaving two simple bands on the screen. The very act of observation collapses the wave of possibilities into a single, definite reality. It is as if the universe is shy, changing its behavior the instant it knows it is being watched. In a purely physical world, this makes no intuitive sense. Why should a conscious measurement force nature to make up its mind? But in a simulated reality, the double-slit experiment is not a paradox. It is a feature of efficient design. It is the ultimate level of detail optimization, a trick used in every modern video game. When you play a vast open-world game, the computer does not render every leaf on every tree in high definition across the entire map. That would be impossibly demanding. Instead, it only renders the precise details of the objects you are directly looking at. Everything in your peripheral vision or behind you exists in a low-resolution, simplified state. The universe appears to operate on the same principle. An electron traveling through two slits does not need a definite position until something, a conscious observer or a measuring device, forces the system to commit to an outcome. Until that moment, it is far more efficient for the program to treat it as a spread-out probability wave, a cloud of potential. The measurement is not disturbing a physical reality. It is simply a command that tells the simulation to stop calculating possibilities and finally render a specific result. This observer effect suggests that what we call reality is not a fixed stage but an interactive experience, generated on demand. It implies that the cosmos conserves its greatest processing power for the parts we are actively examining, leaving the rest in a hazy, undefined state. This profound link between consciousness and the physical world points directly to an even more fundamental layer of the code, a feature that might be the most convincing glitch of all. This recursive patterning we find in the quantum realm extends all the way up to the largest scales of the cosmos. Look closely at a fern leaf, and you will see its main stem branches into smaller stems, which in turn branch into even smaller leaflets, each a miniature copy of the whole. Now pull back your perspective to a satellite view of a river delta with its main channel splitting into countless tributaries. the pattern is eerily similar. Finally, gaze at a computer simulation of the cosmic web, the vast network of galaxies and dark matter that forms the universe's large-scale structure. The same branching, self-similar pattern emerges once again. These are fractals, shapes of infinite complexity that repeat their form at every level of magnification. They are not just curiosities, they are a fundamental geometric language woven into the fabric of reality. The most famous of these is the Mandelbrot set, a mathematical phantom born from an astoundingly simple equation. When this equation is iterated, calculated over and over again, it gives birth to an object of unimaginable depth and beauty. Zoom into its boundary forever, and you will never find a smooth edge, only an endless cascade of intricate, repeating shapes. This is a purely abstract concept, existing only in the realm of numbers. So why does the physical universe, from the branching of our own blood vessels to the clustering of galaxies, so faithfully mirror this mathematical ideal? The prevalence of fractals suggests a universe built not by hand but by algorithm. In computer graphics, this is called procedural generation. To create a massive, detailed virtual world, programmers do not design every mountain and tree individually. Instead, they write a simple set of rules, a seed algorithm, that can generate endless variations of complex terrain automatically. It is an incredibly efficient way to create the illusion of vast, handcrafted detail without the impossible computational cost. The fact that our own reality is saturated with these recursive, algorithmically friendly patterns is a powerful hint. It implies that the cosmos itself might be the product of a generative code, a set of iterative instructions designed to maximize output while minimizing the processing power required. The universe, in its boundless complexity, may be running on an elegantly simple, fractal-based operating system. The same algorithmic efficiency that crafts our reality might also explain its profound emptiness. Enrico Fermi, a physicist present at the dawn of the atomic age, captured this cosmic mystery in a single, devastating question. Where is everybody? The logic is inescapable. Our galaxy alone contains hundreds of billions of stars, many of which are billions of years older than our Sun. If only a tiny fraction of these stars have Earth-like planets, and only a fraction of those give rise to life, and only a fraction of that life becomes intelligent, the galaxy should be teeming with civilizations. Statistically, the cosmos should be a bustling metropolis of alien empires, their radio signals crisscrossing the void like city lights seen from space. Yet when we train our telescopes on the heavens, we are met with an unnerving and absolute silence. This is the Fermi paradox, the glaring contradiction between the high probability of alien life and the total lack of any evidence for it. Many solutions have been proposed, suggesting that intelligent life might be rare or transient, or simply too alien for us to recognize. But the simulation hypothesis offers a far more direct answer. The universe is silent because it was designed that way. Perhaps we are living inside a historical simulation, a meticulously recreated past where we are the sole focus of the experiment. Or maybe we are a prototype, a lone test case running in an isolated server. In such a scenario, the programmers would have no reason to populate our cosmic neighborhood with other civilizations. It would be an unnecessary complication, a drain on processing resources for a simulation that is meant to study only us. The great silence, then, is not a mystery to be solved but a feature of the simulation itself. It is a constraint built into the code to ensure our isolation, or simply to keep the computational load manageable. The paradox vanishes when you consider that this universe may not be a naturally occurring, infinite expanse, but a carefully curated environment. This deep quiet, however, makes a single anomalous signal stand out all the more starkly, a signal that defies all conventional explanation. That profound and unsettling silence was broken just once. On August 15, 1977, a radio telescope in Ohio recorded something extraordinary, a narrowband signal blazing with an intensity unlike any natural background noise, surged from the direction of the constellation Sagittarius. It lasted for exactly 72 seconds, the maximum time the telescope could focus on a single point in the sky, and then it vanished. The astronomer who discovered the printout the next day was so stunned by the clear pattern of the data that he simply circled it and wrote one word in the margin: "Wow." 4 decades of searching have followed, but the wow signal has never been heard again. It remains the most compelling and unexplained candidate for an artificial transmission from beyond our world. But its singular nature is precisely what makes it so suspicious. Genuine cosmic events like pulsars or stellar flares are repeatable. They obey physical laws that produce consistent, observable effects. A one-time event, a flash in the pan that defies all attempts at verification, behaves less like a natural phenomenon and more like a software anomaly. Imagine a vast, complex simulation humming along. For the briefest of moments, a single packet of data is misrouted. A cosmic bit flips, and an unexpected, structured signal bleeds into the reality stream before the system's error correction protocols instantly fix the mistake. Alternatively, perhaps it was not a glitch at all, but an intentional marker. In computer programming, the first simple task a developer often writes is a program that prints the words "Hello, world" to the screen. It is a test, a proof that the system is working. The wow signal, with its perfect characteristics and fleeting existence, bears the hallmarks of such a test signal, a ghostly hello from the architects of our reality, embedded in the cosmic code and triggered just once to see if we were listening. Its very elusiveness is what cements its status as a potential reality glitch, a tantalizing clue that the background hum of the universe might not be as consistent as it seems. This leads us to look even closer at that background, at the very oldest light in existence, for signs of a much larger pattern. The oldest light in the universe carries a secret it was never supposed to reveal. This is the cosmic microwave background, a faint glow that fills every corner of the sky, the cooled remnant of the universe's fiery birth. For decades, the guiding principle of cosmology has been that this background should be essentially the same in every direction, a final proof that the cosmos has no center and no edge. It should be a perfectly random, isotropic tapestry, but it is not. When scientists created a detailed map of its tiny temperature variations, they discovered something that sent a chill through the astrophysics community. The fluctuations are not random. They show a strange and unexpected alignment along a particular axis, a cosmic preferred direction that has been nicknamed, with a hint of dark humor, the axis of evil. This alignment breaks one of the most sacred rules of modern cosmology. It is as if we looked at a vast, featureless desert and found that every single grain of sand was subtly tilted to point in the same direction. In a natural universe, this makes no sense. There is no physical reason for the aftermath of the Big Bang to remember a specific orientation across billions of light years. But if our universe is a simulation, the axis of evil is not a mystery. It is a developer's signature. It could be an artifact of the coordinate system used by the underlying program, a faint scar left over from the initial rendering process. Just as a computer-generated sphere might have a barely visible seam where its texture was stitched together, this cosmic axis could be a hint of the simulation's fundamental architecture, a ghostly imprint of the grid upon which reality is painted. This large-scale imperfection points a finger not just at the structure of space, but at the very moment of its creation, forcing us to confront the ultimate question of what or who might have written the first line of code. The axis of evil suggests a fundamental coordinate system, a grid underlying the cosmos. But what event could have first imprinted this grid onto the void? Our investigation leads us back to the very beginning, to the ultimate singularity. The Big Bang is described as the moment our universe exploded into existence from a point of infinite density, a state where all known laws of physics simply cease to function. This singularity is a profound boundary, a hard limit to our understanding. We cannot see beyond it because time itself, as we know it, began at that instant. In a purely physical cosmos, this is an impenetrable mystery. But if our universe is a simulation, the Big Bang is not a mystery at all. It is the boot-up sequence. Think of pressing the power button on an incredibly advanced computer. For a split second, the system initializes. The screen is blank, the hardware whirs to life, and the operating system loads from a single point of origin. Before that moment, the computer was off. There was no before, no data, no processes running. The Big Bang singularity behaves in exactly the same way. It is the moment the cosmic program was launched, the instant the simulation began processing its first commands and rendering space-time. The fact that we can trace the expansion of the universe back to this definitive starting point and find an absolute barrier to any further inquiry is precisely what you would expect from a system with a finite running time. The initial conditions of our universe, the specific settings for the strength of gravity and the nuclear forces, appear miraculously fine-tuned to allow for the existence of stars, planets, and life. In a natural universe, this is a statistical impossibility of staggering proportions. But in a simulation, these are not miracles. They are the default parameters, the pre-loaded constants chosen by the programmers to see how a universe with these specific rules would unfold. The Big Bang, then, looks less like a chaotic cosmic explosion and more like a deliberate system initialization, the moment the architects of reality clicked run. This leads us to question the very nature of that reality and whether its fundamental building blocks might be simpler than they appear. This perfect calibration of the cosmos is not a minor detail, it is the very foundation of our existence. The fundamental constants of nature are the immutable numbers that govern every interaction from the atomic to the galactic. Consider the force of gravity. If it were even a fraction stronger, every star would burn through its fuel at a ferocious rate, collapsing into black holes before life could ever emerge. If it were slightly weaker, matter would never have clumped together to form stars and galaxies in the first place, leaving the universe a cold, eternal fog of hydrogen. The same razor's edge applies to the strong nuclear force that binds atomic nuclei. A small change in its value would mean that carbon, the essential building block of life as we know it, could never form inside stars. The universe would be devoid of the very chemistry that makes biology possible. These constants are not variable, they are locked in with a precision that defies belief. The odds of this specific combination of numbers occurring by random chance are so astronomically small that they are effectively zero. It is like winning the cosmic lottery 1 billion times in a row. In a purely accidental universe, this fine-tuning is the greatest mystery of all. Why does the cosmos appear to be so exquisitely engineered for our presence? The simulation hypothesis offers a breathtakingly simple resolution. If our universe is a constructed reality, then this fine-tuning is not a lucky accident, it is a prerequisite. The programmers, for whatever reason, set the initial parameters with a specific goal in mind. to create a stable, long-lasting universe capable of producing complex structures and ultimately conscious observers like us. This is the ultimate expression of the Anthropic Principle. We do not find ourselves in a universe suited for life by chance. We find ourselves here because this is the only kind of universe that could have been built with us in mind. It is a universe that was coded for discovery, and the code itself might be far simpler than the reality it generates, pointing toward an elegant, minimalist origin. This perfect fine-tuning of the cosmos is shadowed by an even deeper mystery, one that constitutes the vast majority of everything that exists. Over 95% of the universe is made of substances we cannot see, touch, or directly interact with. We only know they are there because of their overwhelming gravitational influence on the tiny sliver of reality we call normal matter. This is the realm of dark matter and dark energy, the dominant forces shaping cosmic destiny, and their elusive nature makes them a prime candidate for a simulation glitch. Dark matter acts as a cosmic scaffold. We can observe its presence because galaxies spin far too quickly to hold themselves together with the gravity of their visible stars alone. It is as if each galaxy is embedded within a vast, invisible sphere of mass, a gravitational glue that prevents stars from flying off into the void. Yet, despite decades of searching, this mysterious substance refuses to reveal itself. It does not emit, absorb, or reflect light. It simply is. In a simulated reality, this makes perfect sense. Dark matter might not be a particle at all, but rather the underlying gravitational framework of the program itself. Think of it as the invisible mesh, the wireframe model upon which the visible universe, the galaxies and stars, is rendered. In a video game, you do not see the complex polygons and vertices that define the shape of a mountain. You only see the textured surface. Dark matter could be the universe's equivalent of that hidden geometry, the essential structural code that gives form to the visible world. It is not meant to be seen, only to provide the necessary gravitational pull to keep the simulation stable. Then there is dark energy, an even more perplexing force. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is not slowing down due to gravity, as everyone had assumed. It is accelerating, speeding up as if pushed by some repulsive pressure inherent to the vacuum of space itself. This dark energy is the dominant component of the cosmos, making up about 70% of its total energy budget. But what is it? The simplest explanation from a programming perspective is that it is not a thing but a setting. It could be a simple positive cosmological constant, a single line of code written into the simulation's parameters to ensure it continues to run. Without this outward push, gravity would eventually pull all matter back together in a catastrophic big crunch, ending the simulation. Dark energy acts as a cosmic override, a gentle but persistent force that keeps the universe expanding, preventing a gravitational collapse and ensuring the program has the time and space to unfold as intended. Its mysterious background nature is exactly what you would expect from a fundamental system process, a vital piece of the operating system that runs silently in the background, invisible to the user but essential for the program's function. Together, dark matter and dark energy are the hidden administrators of our reality, controlling the large-scale fate of the simulation from behind the curtain. This profound disconnect between the visible world and the invisible forces that govern it forces us to question the very nature of the reality we perceive so clearly. This paradox strikes at the very heart of our understanding of reality. According to the fundamental laws of quantum mechanics, information is eternal. It can be scrambled, transformed, or hidden, but it can never be truly erased. Every particle interaction, every event, leaves an indelible mark on the universe. Yet, black holes present a terrifying contradiction. When an object crosses the event horizon, the point of no return, it appears to be completely and utterly obliterated, its information lost forever to the outside universe. This is the black hole information paradox, a conflict between our two most successful theories, quantum mechanics and general relativity, that has stumped physicists for decades. If information is truly destroyed, it would mean the universe has a fundamental case of amnesia, and the bedrock of physics is wrong. But what if the paradox is not a flaw in physics, but a clue about the nature of our reality? In a computational universe, information is not a physical substance, it is data. And data is never destroyed, it is only archived, compressed, or encrypted. The event horizon of a black hole might not be a physical boundary in the traditional sense. It could function as a data compression firewall. Think of a video game engine managing a vast open world. It does not waste processing power rendering the intricate details of a dungeon that the player's character cannot possibly see. The area behind a solid wall exists only as a low-resolution placeholder until the player opens the door. The event horizon could be the universe's ultimate version of this optimization. The unfathomable complexity of whatever falls into the black hole is not deleted from the cosmic hard drive. Instead, the simulation might simply stop rendering it for the rest of the universe, storing its information in a highly compressed state on the surface of the event horizon itself, a concept physicists call the holographic principle. The paradox arises because we assume the interior of the black hole is a real, physical space that continues to exist. But if it is a simulation, the interior may not be rendered at all. It is a null zone, a part of the program that is deliberately left undefined to conserve an immense amount of processing power. The information is not lost, it is merely marked as inaccessible, tucked away in the system's memory to prevent a catastrophic computational overload. This elegant solution reframes one of physics' greatest mysteries as a simple matter of data management. This holographic view of reality finds its ultimate expression in a principle that sounds like pure science fiction. The universe we perceive, with its 3 dimensions of space and 1 of time, might be nothing more than a grand illusion. The holographic principle proposes that all the information describing every star, every planet, and every one of us is actually encoded on a distant, 2-dimensional surface that surrounds our reality. Think of a credit card hologram, a flat sticker that creates a stunning, 3-dimensional image when you tilt it in the light. The image appears to have depth and volume, but all the information needed to create it is stored on the flat, 2-dimensional surface of the sticker itself. According to this radical idea, our universe operates on the same principle. We are like characters living inside that shimmering hologram, convinced of our own solidity, while our entire existence is projected from a vast cosmic boundary we can never see or touch. This is not just a metaphor, it is a serious proposal born from the study of black holes. Physicists discovered that the maximum amount of information that can be stored within any region of space is not proportional to its volume, as you might expect, but to the area of its surface. It is as if the universe has a fundamental resolution limit, and the data for everything inside a box is painted onto the box's outer shell. This is precisely how information is stored on a computer. The rich, 3-dimensional world of your favorite video game is not magically contained within your monitor. It is generated from a 2-dimensional array of pixels on the screen, each one a tiny bit of data. The holographic principle suggests our cosmos is built the same way, a breathtakingly efficient data storage solution. The laws of physics as we know them, from gravity to quantum mechanics, would not be the primary reality. They would be emergent properties, shadows cast by the complex interactions of information bits on this fundamental, lower-dimensional surface. We are not living in a universe that contains information. We are living inside the information itself. This profound redefinition of reality might even solve a strange and seemingly unrelated cosmic coincidence, one that connects the very large to the very small. These numerical fingerprints appear at both ends of the cosmic scale. The ratio of the strength of the electromagnetic force, which holds atoms together, to the force of gravity is an unimaginably large number, roughly a 1 followed by 39 zeros. For reasons no one can explain, the age of the universe, when expressed in the appropriate natural units, gives a number of a very similar, staggering size. It is as if the cosmos is whispering a secret code, linking the forces that govern the tiny atomic world to the grand timeline of cosmic history. In a purely physical universe, this is an absurd coincidence with no underlying reason. Why should the number describing the pull between a proton and an electron have any connection whatsoever to the age of the entire cosmos? The simulation hypothesis turns this mystery into a feature. When programmers write complex code, they often use fundamental constants or base values. They might define a core scaling factor that is then reused throughout the program to maintain consistency and harmony across different modules. These large number coincidences could be the cosmic equivalent of finding the same mathematical constant, like pi, governing both the shape of a tiny electron orbit and the curvature of a galaxy. They are not coincidences at all, but rather subtle traces of the simulation's source code, hints that the same set of base parameters was used to define both the microscopic and the macroscopic realms. This elegant recycling of core values would be a hallmark of an efficiently designed system, a way to keep the cosmic program lean and consistent. And if the code leaves its signature in pure numbers, it stands to reason it might also leave a mark on the very fabric of spacetime when pushed to its limits. The solidity of the world around you, the very fact that you do not fall through the floor, depends on a single, unbreakable quantum law. Deep within every atom, electrons occupy distinct shells like tenants in a high-rise building where no two can have the exact same apartment number. This is the Pauli exclusion principle, a fundamental rule stating that no two identical fermions, such as electrons, can exist in the same quantum state at the same time. It is the reason atoms have volume and structure, why matter occupies space instead of collapsing into an infinitely dense point. Without this rule, chemistry would be impossible, and the universe would be a featureless, overlapping blur. In the world of video games, this problem is known as clipping, where due to a programming error, two objects pass right through each other, breaking the illusion of a solid reality. The Pauli exclusion principle acts as the universe's perfect, built-in collision detection algorithm. It is a fundamental line of code that prevents particles from merging, ensuring that every electron keeps its assigned place, maintaining the structural integrity of everything from a grain of sand to a galaxy. This principle is more than a physical law. It is an anti-cheat code for reality itself, a crucial protocol that preserves the consistency and stability of the simulation by forbidding any particle from breaking the rules of occupancy. This enforced order, this prevention of quantum chaos, is what allows for a consistent flow of events from one moment to the next, creating the unidirectional river we experience as time. The consistent forward march of time feels as undeniable as gravity itself. We remember the past and anticipate the future, never the other way around. This one-way street, the arrow of time, is one of the most fundamental and perplexing features of our existence. Why does the universe stubbornly refuse to run in reverse? The answer appears to lie in a concept known as entropy, which is essentially a measure of disorder or randomness. The second law of thermodynamics states that in any isolated system, the total entropy can only increase or stay the same. It never decreases. Think of a drop of ink falling into a glass of clear water. It will naturally spread out, becoming a uniform, murky mixture. The system has moved from a state of low entropy, with the ink highly concentrated and ordered, to a state of high entropy, with the ink molecules scattered randomly throughout the water. You would never expect to see the reverse process happen on its own, with the scattered ink particles spontaneously gathering back into a single, neat drop. This inevitable slide toward disorder is what gives time its direction. But why should the universe have such a strong preference for disorder? In a simulated reality, the arrow of time is not a mysterious physical law. It is a necessary feature of the program's architecture. For a simulation to make sense, it must maintain a strict chain of cause and effect. Every event must be the logical outcome of a previous event. If time could run backwards, even for a moment, it would create impossible paradoxes. Information would be lost, actions would be undone, and the entire narrative of the simulation would collapse into chaos. The steady increase of entropy is the program's elegant solution. It acts as a cosmic ratchet, ensuring that the simulation state is always moving forward, always becoming more complex and disordered, making it computationally prohibitive to reverse the process. Resetting the entire universe to a previous, lower entropy state would be like trying to unscramble an egg, requiring an impossible amount of processing power to track every single particle and return it to its exact prior position. The one-way flow of time is a feature designed to keep the story coherent and computationally manageable. This temporal structure, however, places a fundamental limit on what we can ever know, suggesting the simulation may have built-in constraints on information itself. This inherent limit on information is not a bug in our instruments, but a feature of reality itself. Heisenberg's uncertainty principle stands as one of the most famous and misunderstood rules of the quantum world. It declares a fundamental trade-off. You can never know both the exact position and the exact momentum of a particle at the same instant. Pinpoint a particle's location with absolute precision, and its velocity becomes a complete mystery. Lock in its speed and direction with certainty, and its position blurs into a cloud of probability. This is not a statement about our clumsy measuring tools. It is a law written into the fabric of existence, a declaration that the universe operates with a built-in vagueness at its most fundamental level. In a purely physical world, this seems bizarre, even frustrating. Why would nature hide its own details from us? But if our reality is a simulation, the uncertainty principle is not strange at all. It is a necessary and elegant piece of code. Think of it as a core privacy setting or a data rate limiter. Any complex computational system must manage its resources. If an observer, whether a conscious being or a sophisticated machine, could query the system for the complete state of every particle simultaneously, the processing demand would be astronomical. It would be like every single player in a massive online game demanding a high-definition render of every leaf on every tree across the entire map at the exact same moment. The servers would crash instantly. The uncertainty principle prevents this information overload. It is the universe's way of saying that you can only access so much data about any one entity at a time. This enforced blurriness at the quantum level is what allows the macroscopic world we experience to remain stable and coherent. It is a fundamental constraint that keeps the simulation running smoothly, ensuring that no single observer can ever pull back the curtain completely to see all the code at once. This principle suggests that the very act of observation is not a passive viewing, but an active transaction with the system, one that comes with strict limits on how much data we are permitted to receive. And if the simulation protects its core data with such elegant constraints, it stands to reason it might also protect its overall integrity with even more dramatic failsafes. This direct influence of the mind over the body presents a challenge to our purely material understanding of medicine. A patient is given a simple sugar pill, yet they are told it is a powerful new drug. Their belief in this treatment is so strong that their body responds as if it were real, reducing pain, healing ulcers, even altering brain chemistry. This is the placebo effect, a well-documented phenomenon where expectation, not chemistry, produces a tangible physical outcome. In a world governed solely by physics and biochemistry, this is deeply puzzling. How can a thought, an abstract belief, initiate a cascade of healing events that mimic the action of a genuine pharmaceutical compound? The simulation hypothesis offers a startlingly elegant explanation. If our reality is a constructed experience, then the placebo effect is not a biological fluke, it is a feature. It is the mind, a conscious entity within the simulation, using its permissions to alter the local rendering of its own avatar. Our beliefs and expectations could act as a user input, a command that tells the program to adjust certain parameters, like pain levels or immune response, directly. This would bypass the need for a physical intermediary because, in a simulation, the body itself is part of the rendered environment. The power of belief becomes a legitimate interface with the system, a way for consciousness to interact with the code that defines its physical experience. This points toward an even more profound possibility, that consciousness is not merely an emergent property of the brain, but a fundamental component of the simulation itself, perhaps even the primary user. The implications of this mind-matter interaction stretch beyond individual healing, touching upon the very stability of the reality we all share. But the most intimate mystery of all is the one happening right behind your eyes. You can describe the firing of neurons and the flow of chemicals in your brain, but no physical description can ever capture the raw sensation of the color red, the bittersweet ache of a memory, or the simple feeling of being you. This is the hard problem of consciousness, the question of why and how a lump of matter inside our skulls gives rise to a rich, private, subjective inner world. Science can map the brain's circuits with incredible precision, explaining how we see, think, and feel emotions, but it remains utterly silent on why these processes should be accompanied by any experience at all. From a purely materialistic perspective, consciousness is an unnecessary ghost in the machine, a baffling byproduct that the cold laws of physics have no reason to produce. The simulation hypothesis flips this entire puzzle on its head. What if consciousness is not a product of the brain, but the other way around? In a simulated reality, the brain might not generate consciousness at all. Instead, it could be a sophisticated interface, a biological avatar designed to allow an external, non-physical consciousness to interact with the virtual world. Your body, with its senses and nervous system, is the controller you use to navigate the simulation, but the player, the true you, exists outside the game. This resolves the hard problem with breathtaking elegance. The qualitative feel of being is not something that emerges from complex chemistry. It is the fundamental ingredient that was imported into the simulation from the very beginning. Consciousness is not a puzzle to be solved by physics because it is primary, and the physical world is the secondary, rendered reality. This idea turns our entire materialist world inside out, suggesting that the cosmos is not a mindless machine but a shared experience. And if consciousness is the true foundation, then the ultimate glitch, the one that ties all the others together, must be something that consciousness itself can perceive. The most compelling evidence for a simulation is not found in the far reaches of space, but in the simple, undeniable fact of our own existence. The universe appears to know we are here. This is the Anthropic Principle, a concept so profound it borders on the philosophical. It states that any valid observations of the universe must be compatible with the conscious life that makes those observations. In its strongest form, it suggests the cosmos is not just accidentally habitable, but was somehow purposefully calibrated for observers like us. The fundamental constants were set with a precision that defies random chance, creating a stable stage upon which life could emerge and eventually look back upon its own origins. If this reality is a simulation, then this is not a cosmic coincidence. It is the entire point of the program. We are not a random glitch in a meaningless void. We are the intended outcome, the reason the simulation was initialized with such specific parameters in the first place. Our presence here, our ability to question the nature of reality, is the ultimate anomaly, the final and most personal piece of the puzzle. After examining these 21 clues, from the pixelated fabric of spacetime to the ghostly influence of consciousness, a unified picture begins to emerge. The cosmic speed limit, the spooky connection of entangled particles, the great silence of the cosmos, and the eerie fine-tuning all point toward a reality that is logical, efficient, and curiously interactive. They suggest a universe that operates less like a blind, mechanical clockwork and more like an incredibly sophisticated, rendered experience. The evidence does not point to a universe that simply is, but to one that was built with rules, constraints, and perhaps even a purpose. The collective weight of these anomalies invites us to consider a possibility far grander than we ever imagined. Individually, each of these 21 cosmic curiosities could be explained away as a strange but natural quirk of physics. But step back and look at the whole tapestry, and a startlingly coherent picture begins to emerge. The pixelated grain of spacetime, the absolute speed limit of light, the deeply mathematical rules, the quantum shortcuts, and the impossibly perfect fine-tuning are not a random collection of oddities. They are the interlocking components of a single, elegant framework. The simulation hypothesis is not just one speculative idea among many. It is the one framework that accounts for all of them simultaneously. It explains why the universe has a resolution, why it has a maximum processing speed, and why it appears to run on a set of logical, mathematical instructions. It demystifies the quantum world's bizarre observer dependence and offers a reason for the profound emptiness of space. This is not a definitive proof, of course, but it is a powerful and consistent lens through which to view the deepest mysteries of existence. It suggests that humanity's centuries-long quest for a final theory of everything, a single equation that describes all of physical reality, might be something far more profound than we ever imagined. We may not be searching for a law of nature, but for the underlying source code of the simulation itself. This realization completely transforms our place in the cosmos. We are no longer just insignificant beings on a tiny rock orbiting an average star. We become the central characters in a grand experiment, conscious observers whose very presence might be the entire point of the program. The universe is not a cold, indifferent void, but a carefully constructed stage, and we are the players who have suddenly begun to question the nature of the theater. This perspective does not diminish our existence, it elevates it to a level of cosmic significance. So where does this cosmic detective story leave us? The question remains open, a tantalizing possibility hanging in the air. After exploring these 21 anomalies from the Planck length to the power of belief, we are left not with a definitive answer, but with a profound shift in perspective. The simulation hypothesis is far more than a science fiction trope. It is a legitimate framework that elegantly accounts for the deepest puzzles of our existence. It challenges us to think beyond the confines of traditional physics, to consider that the universe might not just be governed by laws, but constructed with code. If this idea is true, it does not make our reality any less real or meaningful. On the contrary, it transforms the cosmos from a cold, accidental void into a crafted experience of breathtaking complexity and potential purpose. Our very act of questioning, of searching for these glitches, becomes part of the narrative. The pursuit of evidence is now the central mission. Scientists are already considering how to test this hypothesis, perhaps by searching for signatures of a computational lattice in the data from high-energy particle colliders, or by analyzing the cosmic microwave background for even subtler patterns that betray an underlying architecture. The quest is to find a signature in the data that cannot be explained by any known law of physics, a telltale sign of the programmer's hand. Whether we ultimately discover we are in a base reality or an advanced simulation, the value of asking this profound question is undeniable. It pushes the very boundaries of human knowledge, forcing us to re-examine everything we assume about existence. The mystery is far from over. It has only just begun. What do you think? Do these cosmic glitches make you question the nature of your reality? Share your thoughts in the comments below and subscribe for more journeys to the edge of understanding.